fun about derivatives. So today the episode is going to be called of power. So why is that? So we're going to try to evaluate. First, we're going to evaluate the derivative of x to the a when a is a constant. So this is actually pretty simple. This is essentially equal to a times x to the a minus 1 when a is a constant. This is called the famous power rule, which is essentially what we can prove by taking the limit. So this thing is pretty straightforward. Or another way is we can let y equals to x to the a, which a is a constant. So now how we're going to do that is we're going to take learn of x, and then we take the a outside. Remember, this is a constant. So what does that mean is we can first take the d over dx. So this side will be 1 over y, and then multiply by the derivative of y, just dy over dx, and that is equal to a times 1 over x. So we can multiply y to there. dy over dx, which is the thing we desired, is equal to y times a times 1 over x, which is equal to y. We can substitute y back in. X to the a times a times x, which is equal to a times x to the a minus 1 as desired. So this is how we proved the derivative of a variable to a constant power. But what if we flip it? So what does that mean is if we want to find dy over dx of a to the x, we need to find dy over dx is equal to what? So this seems kind of intimidating, but we can still use the same way to do it. So if we take learn equal to learn of a times x. Remember, now this is a constant because learn of a is natural log of a, so therefore this is a constant, so we can take this out. So basically the left side is going to be really simple, which is just learn a, and that is equal to 1 over y times dy over dx after you take d over dx. So now we can take y to there. Then we have dy over dx is equal to y times learn of a, just equal to a to the x times learn of a, which is exactly what the derivative is. See, pretty simple, right? And we can see that this is definitely going to increase pretty fast. So if we draw a graph here, sorry, the graph is kind of badly drawn. So we draw the graph here, then we let a equals to 2. Okay, so actually we'll let a equals 3 so that it will increase more rapidly. So when a is 0, so you can see when x is 0, then this function will have the value of 1 of 0, 1. And then 1 and u equal to 3 and 2 u equal to 9. So it's increasing pretty fast, which is how exponential works. So you can see that this will really be accurate. So whenever you see a problem, you have to check that if the answer makes sense, which indeed here it does make sense because the derivative must be really big. Right. So now we're going to jump into something that's more complicated, which we want to find the derivative of x to the x power. Well, this seems pretty intimidating, right? However, we can just use the same ways to do it. So we can let y is equal to x to the x power, and then we take 1. Or we can take log base n, but then it'll be more complicated. So we take ln of y is equal to x times ln of x. Since both x and y are variables, so we cannot directly take the derivative of this, but we can use the product rule. So if we take d over dx, the left side will obviously be 1 over y times dy over dx. Right? We have encountered this so many times. So what about the right side? So right side, if you use the product rule, then you'll first take the derivative of the left side times ln of x, and then plus x times 1 over x, which is essentially going to be equal to ln of x plus 1. So that is what 1 over y times dy over dx is equivalent to. So we can isolate dy over dx out. This is equal to y times ln of x plus 1, which is essentially equal to x to the x power, ln of x plus x to the x power. So this is our derivative. Or we can just be more challenged. We can take log base a, and you should get the same results. So we want to find y is equal to x to the x power. So now if we take log base a y, this is going to take you a lot of work more, and that is equal to x times log base a to the x. So we take d over dx, which is really complicated. So the right side is going to be dy over dx times 1 over 1 over y ln of a, and that is equal to, which a is any constant, which is equal to x times 1 over a ln of x, and then plus, well, I actually did the ordering this wrong, but whatever. So 1 times log base a x. So you can see that this is actually pretty complicated. So we dy over dx, that is equal to y ln of a times x over a ln of x plus log base a x, which you'll get the same result because you can manipulate the logarithms, which is equal to y times x times 1 times a times x and log base, let's see, log base x a? No, I don't think so. I think I made a mistake over here. Yeah, it should be a ln x. No, x ln a. here, so you can just cancel these out. Which after this, you should be getting the same result, right? So I'm not going to do the calculation again, but you should get the same result, which is equivalent to a to the x times ln of a and plus a to the x. No, a to the x times ln of x plus 1. Yeah, I think so. Yeah. So now, what if we have, let's say y is equal to y is equal to x to the z, which z is not a variable. So how are we going to take the derivative here? And now we're just going to use the ln of y again. So how are we going to do ln of y again? So we're going to have ln of y is equal to z times ln of x, and then we take d over dx. You can see that this is actually just a really powerful tool to utilize. So now we have 1 over y times dy over dx. Or you can just skip this step. dy over dx is equal to x to z times d over dx times z ln x. Is equal to x to the z times dz over dx ln of x. And then we also have to plus z over x. Equal to x to z times dz over dx ln of x, and then plus zx to the z minus 1's power. So we are given x and z, and we're given dz over dx, then we'll find the value. Thank you for watching. Have a great day, and if you have any questions, don't forget to leave it in the comment section.